The first 3 weeks of the eruption here in Hawaii, crazy things would happen in the middle of the night. A new fissure would open up and it would threaten a new neighborhood. Thousands of people were evacuated from their homes. I started the Hawaii Tracker Facebook group to help people understand what's going on and get their questions answered.
Hey, how's it going? We're live. This is Fissure 20.
We had hundreds of people all throughout the neighborhoods sending in videos, articles, and images. We spend a lot of time making sure the accurate information gets out.
This is live. There's still lava moving.
They weren't just sharing a story, they were helping their neighbor. If a family member was being evacuated, the group would just jump in and help out. So it was huge. They were watching out for each other.
Hello everybody, thank you for coming. Thank you for the support from everybody.
As we go through this, we're growing closer together as a community. When tragedies like this strike, you really realize how much you need each other.
Hello everybody, I'm Philip Ong, geologist. I'm here with Mr. Dane DuPont. We'll be manning our chats and our stream today. And I'm going to play this, starting from the beginning, this thermal time-lapse of the eruption while I talk here. So we are today on the 33rd day of Kīlauea Volcano's 2020-2021 summit eruption. Began over a month ago, or now over a month into the eruption. And the eruption is still showing us new things. What we're seeing in this image right here is when our north vent was still active, and before the lava reached its same elevation and essentially blocked it with backflow back into the vent. Right, kind of that flow is what's pushing the island in this direction as well, pushing it that way. And then once that happened, we switched over to the west vent, which was already active earlier in the eruption, but wasn't nearly as productive as that northern vent. So we'll see it come here soon. You can see the island is kind of moving around. Here's our west vent. You can kind of see that the direction of flow changes. Now the lava is all flowing off in that direction, right? And kind of circulating around and coming around and actually pushing the island more from that direction. So this island has come. This is the big island floating in the lava lake. And it's going to do a little spin here, and that's kind of entering this new phase of 2021 when we have no longer this active circulating lava lake. You see all the lava circulating all the way around the whole back part of the crater here. Right, this is Halemaumau crater inside of Kīlauea volcano, the summit pit. And so here our island is getting pushed back towards our main vent. It's going to rotate. And once it rotates and becomes long way against that vent, it seems to disrupt the circulation a little bit. And so now lava is going to flow out only through the sides and then come back around to the middle this way and this way. And that seems to have kind of caused some stagnation in this whole back area over here, which will shortly form a crust that maybe are nucleated by these other islands, these other pieces of lighter, less dense rock that formed when lava met the water initially when eruption first began, that first flash of steam that began the eruption there. So I'm showing you guys this movie because what's happened recently is much different than is happening so far, right? So this is kind of the view still. I can maybe fast forward a little bit. Fast forward a little bit. And you can see now we're forming a crust here on the backside. And we're still having overturning events where lava is still reshaping and reforming, coming up through those cracks, breaking the crust, replacing it with new crust. That's still happening at the point of this video here, which is about 12 days ago, where we are in time lapse right now. So I'll fast forward a little bit because this kind of stays fairly steady with activity growing at the west vent, and of course the perch walls, the perched edge of this lava lake still overflowing down in areas like this, and also over here. Right, that's all things we talked about before. But what the real change is what's happening as we approach the evening of the 18th here. So and still see quite a lot of lava flow coming around, and not as much coming around the backside from either direction. But you do still have this kind of border zone where the crust is forming and still getting overturned as the lava flow comes around. All right, so here we go. Here we're on the 18th. And notice how active the lava still is. And what's going to happen is we have a natural deflation-inflation cycle, a pressure cycle in a volcano. And this is something that in the past has interrupted other eruptions and could even stop lava flows down from Pu'u'o in the past. So we were kind of speculated that that might happen, and here it goes, right? Right there, we see the vent actually stops putting out lava for a few pulses. Maybe it's going under the crust. And the whole crust kind of becomes a solid color, and then you can see it's replaced, and it's spreading off in these directions. And you can see here at the end it's become more active again. So that's the part that I wanted to focus on there a little bit more. And so let me pull up this video that we were showing. Showed you guys as a separate little clip as well, but this is juxtaposing the S1 cam, which is the visible camera, against the thermal camera. And so there's a little bit of a different view here, because from this bottom point of view, north is something like this, and in this upper view is something like this. So we have slightly different views, but you can kind of see the pulsing that's happening as lava is coming out. The crust is overturning. And what is crustal overturning? And this is where I wanted to show you guys some of these videos from the USGS of what these sequences actually look like. So that's at night. This is sped up 20 times, whereas those past videos are somewhere in the order of 10,000 times. So this is way slower than the actual time lapses I showed you guys, but it's still fast enough to see the geologic process happening, which is what we need to do. It's kind of the difference in time scale between people and nature. It can be really small, really big, really fast, really slow, and in this case, everything happens really slow. We got to speed it up to really understand what's happening there. You saw that whole crust being all the way replaced, and now everything is solid once again, until at what point we actually have that crust trapping the heat. It builds up heat, and maybe at some point you can break through some gas and kind of pop it up that way. But what we're seeing is not so much that process as much as it coming in from the vent side and kind of knocking pieces of crust, which is kind of a propagating effect which continues on and on. So all right, let me pull this back over on the screen so you can see all of it, and I'm going to show you guys this is part of a deflation-inflation cycle that began over here on the 19th. And ended earlier today. You can kind of see we're actually on the upper part of the uptake of the pressure coming back up. The scale we have here is an order of 6 microradians of drop, so that's more typical. And the length, the duration here is on an order of a couple of days, and that's more typical as well. We'll look at the tilt plot here shortly on the USGS page, but as we proceed through this, I wanted to kind of just make sure you saw that. So in fact, let's go to that now. Let's finish off this thermos here, because I think it is worth seeing that a little bit more again. All right, so we'll focus just on the thermal camera now, the F1 camera, and there was our side vent that was just active, and here is our south vent shutting, or west vent shutting off. You can kind of see a little bit better overturning pulses to kind of start off from here and move in that direction and move in that direction. Right, kind of what it takes is breaking that crust the first time, and then that propagates all the way around. All right, so here's our view from the S1 cam looking from the south. North is kind of in that direction over there. And so you can see there's still lava coming out of here. You can still see red in the vent at all these points in time, but it's not as clear when it might be flowing out underneath that crust. And at the other times it appears to be moving on top of that crust. Right, so that's interesting to see. So one last time here, side by side, you can watch these two cameras simultaneously. All right, Dane, everything all right over there? I may have possibly lost Dane, it appears. But all right, let's put that away. And let's come over here and show you guys the most recent 24-hour animation put out by the USGS. And so you can kind of see that in the last 24 hours, it's been much more active than it was. You can kind of see at the beginning of the sequence, we actually have here that frozen, all one color lava lake, which means it's one kind of solid crust, probably very thin, but kind of trapping the heat underneath it. And then we kind of see it cycling back to this. Most of the day, it's been putting out lava kind of similar to the old rates, and you just kind of see that pattern here. It's more obvious that it's flowing in these directions, and the areas back over here are doing more of that overturning process, right? And lava flows coming out of here, if they did happen to go on top of a crust, would then break that crust and start that domino effect. It propagates all the way across. So that is our thermal camera there. And we'll show you guys some of the other cameras. Here's that S1 cam as it looked a few hours ago. Let me reload it here and see what it shows us. You can kind of see there the S1 camera. The vent is clearly putting out a lot of lava. It's flowing both to the south and to the east over here, and going all the way around the backside of the island on both sides over here. So that's still as it was earlier today. And the view from the KW camera, which you don't check as often, but there it is. You can kind of see that same effect, that same pattern. All right, so moving on. Here's a photograph that's put out by the USGS Hawaiian Volcano Observatory today of Halemaumau West Vent, taken yesterday. And kind of zooming in, you see it in a little bit better resolution, those same things, same features we're looking at. You know, here's this massive cone of the west vent that's formed as lava is kind of spattered out of that hole, right? And kind of come and landed on the sides one way or the other, or overflowed, or in this case, they say it actually was forming a small little lava tube and actually overflowed it to go over top. And so there's kind of an upper path and a lower path that might still feed underneath the crust. You guys probably remember when we had that dome fountain when lava was not apparently going in, but it was still feeding that deeper pathway going through. So that still exists down there. And it's hard to know exactly how much everything shut off at that point. All right, I think I have Dane back. Yeah. How's it going, Dane?
Yeah, so as soon as we started, my camera froze. The live stream, so I was trying to get it back up, and that started a whole bunch of issues. But yeah, back now, and we are going to be taking questions.
All right, awesome. So yeah, thanks Dane for manning the chat and the questions there, and let's see if we can keep them around a little longer. Yeah, that's how it goes these days with everything on the internet. Sometimes there are issues. All right, so moving on here from our most recent view of the lava lake, we're going to go to deformation data. Yeah, and by the way, if you guys do have questions, put them in the chat, and Dane will be taking them, and we'll break for questions at some point shortly in the show. So the past 2 days, you can see that we've gone up quite a bit. Let me change my color here to a easier to see red, and you can see that after kind of bottoming out and a slow decline, we've had essentially a fairly steep upward rise. And so it's easier to see this on this 1 week plot where you can kind of see the smoother curve right there, right? So this is a more typical pattern than one we had before. I'm going to go back to the past month and zoom in on it so you guys can see here. So we can kind of compare this one that we've just come out of, right? This is like this was our stable pressure, and then we deflated, and then we inflated, right? And probably come flatter again at some point. It's interesting to see that there is still kind of possibly an upward trend right here, because our previous deflation-inflation, you know, seems like either it has an upward trend afterwards, or it was a very unusual longer deflation and a much longer inflation, right? So you can kind of see that the actual scale of it's not quite as deep as the one we just had. So that's interesting. But and the duration going in this direction, the one we have now is clearly didn't last as long as that. So typically this is something that has been described before, right? We also have these smaller variations in here. You can kind of see a little wiggle, a little wiggle, a little wiggle. This spike is an earthquake. And those things show up as well. So as we brought up in previous updates, here's a plot from the Hale Ma'u era, and I want to say 2009, and yeah, 2009, and you can kind of see a similar deflation inflation cycle, and then I have a couple of these little V-shaped gas pistoning signals kind of on top of it as well. And if you were to keep looking, you see that there's quite a lot of deflation-inflation events happening over time there. And this is believed to be the movement of some denser fluid downwards, essentially blocking the path upwards, right? So everything kind of deflates as that slug drains down, and maybe more gas-poor magma that's in the area, right? You know, whether the gas is bringing out the magma through the actual west vent and pouring it into the lava lake, but it's also bringing out gas from the magma also without bringing magma out. So you can have magma degas at different parts in the system that then want to drain back because they are more dense, having less gas. So that's the kind of process happening there. And so the big question then is, you know, what's going to happen next? And so I'll reload it here and see if we've shallowed out anymore. And I don't see anything, but we'll probably shallow out. But then the question is, are we going to go up? Are we going to go down? Are we going to stay stable? What happens after that? All right, and so kind of focusing on a tilt still, one interesting thing is if we look down at Pu'o'o, we see that there is no deflation-inflation event signal on there. We actually have this little step down that occurs when an earthquake happens. And it seems like it adjusts back upwards from whatever, maybe the thing tilted, and it tilted back at a few days later and kind of reestablish itself. But you don't see a big deflation-inflation event. So that leads us to believe that there is not a pressure connection between the summit and Pu'uo'o at this point. There certainly is a rift zone, a pathway, right? But it's not pressurized at this point. All the pressure flowed back towards the summit at the beginning of the eruption and has not refilled. So we're still losing more pressure than we're gaining overall. All right, that's the kind of the point of it. And that's if we go back to the big picture here on this tilt plot. It's a little bit difficult because it's only showing us the past month. Only showing us a past month here, but we actually had here at the back end of this, when we started off, about a 45 microradian drop. And came all the way down before it came down and over and then bumped up, and that's what this point right here actually happens to be. All right, so no signal at Pu'uo'o. Interesting to note. As far as the depth, USGS report today, 204 meters, 669 feet. So it's still slowly creeping up. It certainly, well, let's look at this a little bit more closely. They actually have now on their main current eruption page, USGS Hawaiian Volcano Observatory, they have now added to this depth plot. And so we have here illustrated green as observed depth was manually measured early on, and then they have added a blue line for a raw lake depth. And if we go down here to the description, we'll see on January 8th, 2021, a novel laser rangefinder was stationed at Kīlauea Volcano Summit. And so that's the one that's continuously measuring the distance and telemetering the data to HVO in real time. And so they actually are averaging it every 3,600 seconds, right? That's one, what is that? 60 seconds, 60 minutes, 1 hour. 1 hour running average. And if we kind of zoom in here, we can kind of see that there was a little bit of a drop off going down, presumably when we had that deflation. and since then it's come back up, right? So that's kind of telling us in real time there the elevation of the lava lake. So that is awesome, continuously updated. And we'll scroll down here and look at the gas measurements. There hasn't been any new gas measurements since our last update. There's been quite a lot of rain up here, and it's while geologists don't mind going out in the rain, some of the measurements just don't work if there's water falling through the air, obscuring your instrumentation, your UV source, and all of that other stuff. So that is sometimes just how it goes when you have a little bit of a data gap. And so that another question right here is, what is the gas going to do? Will it stay stable? Will it drop off? Or will we see these cycles as well, potentially, right? If we can see enough data, enough resolution in there. Speaking of the gas, we will reload our purple arrow, which has our most data points of any site that we have here. And there's a lot of greens, but there are still a few yellows and high numbers in these green values in the South Kona area and down in Ocean View as well. And so looking at the VOG forecast, you can kind of see that there's quite a lot of VOG lingering in the Ocean View area. The Mauka side, the uphill side, right down by the coastline, it seems like it's okay. It seems like there's a big gap down there by the coastline. It's more that uphill side right over there. That is the problem area. Okay, and then coming to earthquakes for Kīlauea. This is the last day. You can kind of see that we still have that activity over here in Pahala in the south. Those deep earthquakes, and we have a couple Mauna Loa earthquakes. One that happened earlier today is this 2.0 that happened above sea level, so within an actual stack of the volcanic lava flows here. All right, so that's gonna do it for Kīlauea today. We are gonna cover Mauna Loa as well, but before we do that, we can take a break here and take some questions.
Right, and we do have several questions coming in. Before we get into that, we are brought to you by Hawaii Tracker, hawaiitracker.com. Best way you can support us is to be able to share this video. We don't have an advertising revenue of many of the bigger news organizations out there. We rely on word of mouth more. So if you like this content, you think more people should be able to see this type of content, your share goes a long ways. Secondly, hop on hawaiitracker.com, become a member. That really helps keep the community growing that we're trying to bring together. And the third big way to be able to help us is making a monetary donation on hawaiitracker.com/support. That goes goes to being able to provide this kind of content, continuously. We do have some donations if you want to go through those now, Phil.
Yeah, I think that's a good idea.
All right. Well, we have some new donators, GGS, Janet K, James P, Cheryl T, and Janet R. And then Lori Mae H came in big with a $1,000 donation. That really is going to, help us keep going. And we really appreciate that kind of stuff. That's not a new one, but that is, one that we had. So thank you guys. So let's get into some questions. They've been, Lori Mae is a longtime supporter. So yeah, let's get into some questions. We have some good ones here. Wherever I put them, there we are. So going back to prior to 2018, and let's talk lava lakes, right? Because there's been a few questions just generally speaking about lava lakes. So one of the questions is from Brady is, does the lava lakes have historically periods of dormancy where they come and go? And that also dovetails into the second question, which is from Eddie about Pu'uo'o's lava lake prior to the 2018 eruption. Did it have one, and kind of what were its characteristics?
Right. So yeah, Kīlauea has a long history of lava lakes. You can go back and check out. We have a historical video where we cover some of the historical lava lakes in the crater and some of the historical islands floating in those lava lakes, because there have been actually quite a lot of those as well. But the short answer is yes. There have been times when lava lakes have been intermittent. There have been times when they've been long lasting, where they've lasted. In 67 to 68, it was 9.5 months We had, of course, a 10-year eruption, 2008 to 2018, and you kind of getting into that might be part of the discussion here only because the precedent, I mean, the reason that lava broke open at the summit in 2008, after having already erupted at Pu'o'o since 1983, is because there was a long-term buildup of more magma coming into the volcano over years and years. And that manifested in first breaking open the Mauna Loa lava lake, sustaining it for a full 10 years while still erupting out of Pu'o'o. And eventually, that long-term magma pulse is what kind of caused the whole 2018 eruption, right? That pressurization that spread across the whole volcano to induce the magnitude 6.9 earthquake and everything else that came after that. So, while there have been times that there have been intermittent in the past, we have to look at the question of the long-term supply rate, and maybe the 2018 eruption didn't change anything as far as the supply being more from below. We're still waiting to hear back on that. And if that's the case, then it could be a longer lasting one as well. We think of the era between 1823 and 1924 as mostly continuous 100 years of lava lake. There were a few years in there where it wasn't continuous, and there were times where it wasn't always reliably documented. That it was there. That's the tricky thing about some of this history, that it might be not quite so detailed as we would like in certain times. So there are history of both intermittent lava lakes and continuous ones, maybe not quite 100 years, but decades for sure, right? We saw the last one was 1 decade, 2008 to 18, that kind of followed a whole bunch of magma pressure, right? But, even if we relieve the pressure at the surface, we still have that pressure rising from below, perhaps in a long-term trend there. And so that might indicate that it could last a little bit longer than I might have originally put out and expected, and I am surprised that it has gone on this long after what it was not showing any signs for 2 years after 2018 that anything was happening apart from inflation and INSAR and that kind of thing. But it was December 2nd we saw the first crack of an intrusion, and at that point we knew, okay, well, it's go time. So right, a long answer there, but that's kind of the detail and the interesting things that come with it.
So we're staying on Kīlauea for right now, and specifically at the summit. So Catherine from Facebook is asking about a little bit of clarification on what you mean by inflation at the summit. Like, is the entire summit inflating? Is it the entire caldera? Is it the downdrop blocks inside the caldera? Like, what's the general extent of when we say inflation at the summit or something along those lines?
Right, okay, so let me think of the best way to show you this. I might try to open another window hangout here and switch over to it to show you guys. Right.
There's a few ways to demonstrate this. I'm not sure what Phil's going to pull.
Well, I'm just trying to pull up the USGS monitoring site here. Because what was I think I lost my train of thought here. Help me out.
Showing deformation. You're showing deformation at the summit. Basically, what's the extent?
So we're going to turn on all the tilt meters here, and I did that by clicking this phase thing, and I can it's hard to see all of them, but you see Kīlauea Iki is showing those same kind of deflation and inflation cycles kind of over here on the side over there. So you can see that in the caldera area, right, which is the caldera is this area right in here. So that inner pit of Halemaumau is in here, and the lava lake probably fills about that much space in it, something like that. And so the station that we look at most of the time is this one that's right over here at Uekahuna. Sometimes we look at the Sandhill station. It's kind of over here. That one's also showing that inflation-deflation cycle. As well, the station over here at the summer camp is one we've occasionally been able to use in Kīlauea Iki. So we're seeing it essentially in this summit region is we see most of that signal occurring. The long-term trend has been a deflation across most of this area. And you might imagine there might be a little bit more localized effect of inflation more somewhere in here, right? You can imagine when we had that intrusion, it happened in this area over here. So our most intense inflation might be happening somewhere in there like that. And that's kind of the range of it. Any more suggestions, Dane?
That works. I think we're just trying to do generalized. One other way was the one that came to mind immediately was just INSAR. like pull up a generalized INSAR, but it doesn't have to be close. But I think you basically,
Yeah,
we're able to do it John Madden style and make it work.
We'll talk about this, and INSAR is a satellite measuring technique, and so we'll talk about this here shortly as well. And the reason we're going to wait on that is because the Volcano Awareness Month talks are. I would be surprised if there's not at least one INSAR image of this eruption on there. So once that is released, we'll have it to actually discuss. And until that, we'll cross that bridge when we get there. And at this point in time, we'll kind of just leave it at that, right? But that gives us more so everywhere the radar hits the ground, not just where the instrument is put in the ground by the scientist. And so it's a much more detailed picture in some ways, but it does have its own range of errors and limitations as well, like not being able to see through trees, kind of thing. Unfortunately, this area is all barren.
Yeah.
On this
right.
Mostly on the western side over here, a lot of forest over here. So we'll see how that shows up.
Right. So one more question about the lava lake. Is there any chance of we've been talking about it's a perched lava lake in some instances. Is there any chances of the rim of that perch collapsing?
So we're talking about this rim that's kind of over here. It's most easily seen right along in there.
Right, that one.
Yeah. Sometimes those do have small little breaches, but it's just going to flow into this little trench, and then this is a big uphill over here on this side again. So it's got nowhere to go except to fill in this void that's kind of lower over here, right? But I think it's interesting if we look at if I speed up here. So actually, let me show you this one. Let's go back to the last 24 hours here from the USGS time lapse. And you can kind of see that what's happening, which I find interesting, is that we have a perched rim that goes all the way around the back of this lava lake over here as well. And we also have a trench that goes behind it over here. And what appears to be happening is that lava is squeezing out against the crater wall. Right? You can see a little bit popping up through the crust right in there too. That's interesting. And one of the first lava flows we've seen on this crust pops up right in the middle, right in there. But otherwise, it sneaks up along the edge and is actually lifting. If we were to cut this as a slice, what's like a trench over here, a crater wall, a trench, a perched wall, and then a lava lake with its little islands in it. And another trench and a crater wall over here. Right, it's actually lifting up that entire thing from the bottom up. And so at that point, the actual wall the levee doesn't really hold much in. It can it can leak up. It can go over top of here, but it can also leak up. In fact, I think I see this right over here in this right little edge. I wonder if I can zoom in on that some more. I'll zoom in on a spot for you guys so you can see. Look, it's hard to tell what these pictures are. Maybe not often. Maybe it spills over from over here and goes in, but actually it looks like lava might pop up over here before that happens, right? So it's actually pushing under this as well. So really, this is just a little surface feature. There's lava underneath even over here. Maybe that, and it's all in a big bowl, anyways. So interesting to think about, right? It could breach that out, but it's just a matter of at that point breaking a crust that has a perch shape on it, because there's lava flowing underneath it all the way to over there.
Right. So we got two more questions that I'm interested in. Kind of interested in what you'd respond to this one. Zeus from YouTube is asking, is this the deepest lava lake in Hawaii recorded history?
The deepest.
See, because the thing that's weird to me is like I always envisioned the lava lake that existed, and maybe I'm wrong on this, but I always envisioned it prior to 2018 eruption as just basically the top of an open conduit, right? So you're just seeing a almost seemingly bottomless, so to speak, cylinder, or not a cylinder, but a conduit coming up, and whereas now you have an eruptive vent pouring in to fill the lava lake. So it's not, it's more like a lake now than the one we had previous. Is that, what's your thoughts?
Yeah, so they actually, it's interesting that you mentioned that, and I'm trying to look for something here on my computer as we're talking, because I know that they made a point to scan the Kīlauea crater after the lava lake drained in early May of 2018.
Right.
So I have that video here somewhere. If I just take a second to find.
I do have a comment about that video, and you do find it, pull it up.
Yeah, I think I have it here. No, that's the wrong one. It's an earlier one, and
like we have all these pictures. It's just like on the spot, trying to remember, like, oh, where did I save that thing? Or, you know, when we try and pull them up on the fly.
Right. I'm not sure where I'm finding it here. Sorry, you guys. I'm sure this is riveting to. But I can't talk to something that I forget to mention. You know, Pu'u'o did have lava lakes for many years as well, and they kind of came and went. Some of them lasted a couple years, and so they actually were sustained in that way. But they were a lot smaller, and they were a lot, the source there was shallower, so they weren't as deep as this Kīlauea lava lake, which is why we're kind of focusing on this one as maybe a more interesting one. I'm not finding it right now.
I'm not seeing it really easily as well online when I'm searching for it. I know what you're after. I just.
Yeah, I have it here somewhere if I keep looking enough.
Well, that's probably the thing that that model, that DEM, I believe you're going to pull up.
Mm-hmm.
The 3D model. The one thing that I always thought of is, you know, it showed a bottom to it, but the amount of stuff falling into the conduit when it drained made me think immediately. My gut reaction was, oh, okay, it just clogged it up. Like all the debris fell in, found a choke point, clogged it up, and made like a false bottom. That was like when I saw that thing, I was like, oh, okay, that's just that.
Yeah, certainly there is certainly is clog there, and I finally found it and put it up on the screen here. This is the 3D model Kīlauea GeoS put out.
Prior to 2018.
Yeah, so this was taken in May. So the lava lake had just drained, and the collapse. So there is a bunch of rubble at the bottom, or maybe there's even still lava down there. In fact, I want to look at this. Pause it.
Yeah, it kind of looks like it.
I think there's still lava down there. It kind of drained down to that far, but they're trying to get an idea of the throat of it. So, but that's an example, right? In this case, the lava is all the way down here, and it had, before that, it was spilling over the edge up here. So it seems like that one. It's hard to know the scale, but the lava surface now is still something like 1,500 feet below where it was at that point in time. So I would bet this one, and if we go back to the historical record, there were other times when we had similar elevations of Kīlauea caldera with very deep shafts, and lava lakes would drain away. People would see them. In fact, there was one good one from 1894 collapse. Maybe you could find that one at some point too.
Right.
But it is in our historical videos there, and then that shows that there can be many thousands of feet. Yeah, so I mean it's getting there, but probably if it had a steeper cylinder rather than a flared cone, you might get a much deeper lake. And so that this may not be the deepest one, even though it's amazingly deep and and it's amazingly huge, and still hot and churning. That's the interesting thing there.
Right. Just interesting to think of like the how deep was prior to 2018 lava lake? How deep was that? Right.
Right.
It's like this one, we actually know how deep it is because we saw it before it formed. Right. Now it's like conceptually talking about that, it's weird. All right, so jumping into the next one. And
that crater formed from the bottom up, right? So that's why we don't really know. So we don't know
exactly.
Exactly how it wasn't top down; it was bottom up.
So with regards to the lava lake still, what does the recent testing of the lava, which was done by USGS and published in the most recent Volcano watch, telling us that it was quote unquote old lava? What does that mean? for
we're gonna cover all the Volcano Watch here at the end of our broadcast after we do Mauna Loa here. So we'll talk about a little bit more about that. And it really depends. Tuned. We need a little bit more information. It's kind of the bottom line, and this may be just the beginning of the story. Is also the teaser for that. So, should we move on to Mauna Loa?
Yep.
All
Sounds good. I'm got you at the end of the show for another round of questions.
All right. So Mauna Loa. We were just looking at the earthquakes, and where's my earthquakes page? Here's my earthquakes page, and you can kind of see over the last couple of days, not a couple near the surface of Mauna Loa, but that's normal background. And in fact, what I want to show you guys is kind of earthquake rates for the past year of Mauna Loa, and so we're over here at the right end, kind of still a low trend since the Kīlauea eruption began, kind of at a lower pace there. It was a little bit higher before that, but even that time wasn't as high as some previous peaks, like the mid-year around August. Just this in particular graph right here. And where there's earthquakes happening, so here's the automatic USGS plot, and it shows all the little ones too. And you can kind of see around a summit region, there's that area to the northwest of the summit, that's a little cluster. A bigger one happening over here in the upper southwest rift zone. There's kind of been a lot of adjustment around here, but that's kind of expected. You see a lot of big craters over here as well as one in the northeast, right? But certainly we're seeing adjustment, earthquakes happening over there as well. And then kind of some other ones over to the east and kind of scattered all throughout, all over the place here. It's kind of just the background level, really. There's not a whole lot there. It's a slow change. As far as the GPS, we can kind of see that this was the Kawiki earthquake sequence that happened right in here, which was in October, an adjustment of Kīlauea, which affected Mauna Loa. Mauna Loa then had a chance to kind of exhale, and then now she's inhaling, she's filling with lava once again, heading upwards. With a few still little excursions, you kind of see these from time to time, various points in time, right? It's rare to see it kind of go up straight, but this sequence was certainly not part of the pattern. Although now, still in a slow rise, no signs of change, nothing reported by the USGS. There's not really much to speak of here. We're kind of just touching base, and we can kind of go from there. So Volcano Watch is something that's been brought up here, and that's our first peek into the chemistry of this current eruption. And I encourage you to go and read the whole article. I'm not going to read the whole thing for you guys. I'm going to point out some of the interesting things here. So I'll start off just with showing you guys this magnified view of what they're measuring here. And this is like Pele's Tear here in the middle. I might have to go back to my yellow. Pele's Tear here in the middle. You see some of these almost like Pele's hairs, long, like a natural spun fiberglass. It's like a piece of cotton candy that's spun off from lava, and it gets wafted in the wind and carried up. And you can also have bigger chunks of frothy lava that are carried on those really massive thermals. The gas is really billowing out of there, right? And possibly more so when lava was going into the water in just early couple of days, putting up all that giant steam cloud. So that's interesting. That's kind of the plain regular microscope view. And then they've also done electron microscope scans on these things. And so this is measuring how much iron, and it's kind of, they can then interpret whether it's minerals of plagioclase or clinopyroxene, whether bubbles, or whether you have, in other cases, olivine crystals. Epoxy is the glue that they use to actually put the piece of rock on the sample to actually run the scan on it, right? And so that would have been like an air void, gas void that was then filled in by the glue later on. So that's kind of what those actually look like. There's all kinds of interesting microscope science that I will refrain from going too far in the weeds on that here today. But I want to kind of scroll down here and point out maybe some of the more interesting part of it here. So they do say here, the little part I'll read, that the new Tephras have magnesium oxide contents of about 7 weight %, similar to the previous lava lake in 2018. This indicates that the current eruption did not begin with fresh, in quotes, hot magma entering Kīlauea's shallow summit reservoir. Instead, it's coming from that shallow summit reservoir, likely drawing magma from the same shallow source that fed the 2008-18 lava lake. Okay, so that 7% is the number I'm going to take out of there. And I'm also going to go down here a couple paragraphs, and I'm going to show you guys a little bit more. The newest crystals are typically 0.02 inches in diameter, half a millimeter in diameter. and have relatively low forced to right values of 82%. So that's kind of the one of the ways that we measure this. So what I'm going to do here is I'm going to lean back on the real experts on this. And it looks like maybe we have lost Dane to his camera again, but researchers at University of Hawaii Hilo and Hawaiian Volcano Observatory, Dr. Shiro Ganseki, Alpaka Lee, Thomas Shea, Stephen Lundblad, Ken Han, Carolyn Parchetta, a mix of USGS, HVO, and University of Hawaii authors, researchers here, collaborating on a chemistry of 2018. And what they essentially were finding, I can zoom this in here, is that they were using this kind of model of our volcanic plumbing system. But if I zoom in here, let me zoom in. Please let me zoom in. If we zoom in here, we have our summit caldera right in here. And this over here is our shallow reservoir right there, right? And so they've actually drawn it in this particular image as being most of the way empty. But we know from studies from also USGS employees, Anderson et al. Specifically, that the caldera began collapsing when it had drained only 4% at most. And the most of its, the range of complete draining for the eruption is somewhere between 11%. So it might have drained only 11%. It may have drained as much as 33%. So at the very least, this thing was 2/3 full following 2018. I'll fill it all in there, right? At least that. And then it's kind of refilled the rest of the way and put a finger back up, and now lava's being released here. So that's kind of status quo, right? That's all that means. It means status quo. There's also this deeper source over here, right? That South Caldera chamber that can have slightly deeper, slightly hotter signatures. And what they're saying is it's consistent with what we see more so of here, less so of here, and definitely less so of anything that might come from below and any other bypassing the system entirely. So it's telling us a couple of things. One, that we're actually working within the system, not breaking out of the system. And it's telling us that the system is as it was before, where the deeper chamber feeds the shallow chamber, and a shallow chamber is the one where the lava is actually coming to the surface from, is right there. So it's kind of nothing new there. As far as 2018, there are different phases of the eruption, which are interesting to kind of revisit in some very, very brief detail, but kind of the yellow was initial phase and the blue is a later phase. The blue lava is the one coming from the summit area over here. If I move over to the side over here, you can kind of see that there were a couple pockets, 1 and 2, that were other pockets of magma that were pushed out, that were much, much older magma. And that's kind of something we're not seeing here, of course. In these cases where there's magma sitting underground for decades, possibly centuries, right? This might have been a centuries old pocket of magma over here. And so we're not seeing that. We're seeing magma that's actually coming from that normal place, right? And so the way they actually measure this through olivine crystals might look a little intimidating, but it's all right. I'm going to let her explain, Dr. Ganseki, in her own words here, but I'll talk you through just how it's set up here. Going in this direction is just a date, right? So this is the beginning of the eruption, 2018, on the beginning of May. And as time went on, what they were measuring on the side, 2 different plots here. This is the magnesium oxide in glass. And down here is a forsterite in olivine. So what I'll do is I'll just kind of set it up, and I'll kind of give it to her in a short 1-minute clip here and show you guys. First of all, we came in at 7. So at 7, so before the 2018 eruption, pool lavas were falling in this range, slightly less, slightly cooler, after having moved from the summit, which fell in this range up here. So kind of normal. 7 is normal in that, as far as what we see, and as far as it's about the highest we've seen anywhere. So the 7 is not telling us anything more than that, apart from it's kind of normal in that sense. What's more interesting is a forsterite in olivine. We're at 82. 82 falls in the high end of this pre-existing summit cluster of Halema'uma'u. Pool once again a little cooler. But look at the range of the first older lavas in 2018 before the fresh lava came and replaced it. The blues are the fresh lava over here, right? So this early stuff was all much cooler than what we saw over here. So we don't have this phase at all in our eruption happening now. We've kind of skipped ahead to this kind of population. Now, what was different also in 2018 is that we had these much hotter values up in here, right? And so what I'll do now And just kind of scroll down here, you guys can see days since eruption onset here in the bottom, 0, 10, 20, 40 to 100 days over here on the right. And what I'll do now is I will let Dr. Ganseki explain this herself and play for you guys this little clip here.
Those olivine crystals floating in there, this is going to be about how much magnesium is in your olivine. Right here in gray, those are the Holy Mountain lava lake samples. Whoa, had a little bit more variety, that's these little black triangles, but they're all pretty closely matched in chemistry. So the eruption begins down here with the yellow guys, very cool. They've been sitting there crystallizing, great, that makes sense. Next batch, okay, they're getting hotter, already starting to overlap with cool, that's interesting. And then we start getting into here, and all of a sudden, about 20 days
maybe it'll play.
We find olivine with almost 90% magnesium. Now that, you need a magma of about 1300 degrees to get that. And this eruption is...
So I don't know if you guys can hear the sound there. Maybe I'll just repeat a little bit of what's going on. Just kind of using a laser pointer here, but I'm just kind of looking at that same graph. What she's saying is that 20 days into the eruption or so, they detected these very, very high forcerite contents of very, very hot magma. And she says that this composition of forcerite requires magma about 1300 degrees, which requires it to be from a deeper, hotter source, not that shallow chamber. So 2018 was unusual in a sense where they did detect this deeper, hotter signal where we don't usually detect that. In 2017 and 18, the Mauna Loa lava lake was pretty consistent, right around there, 80, 81, and Pu'o a little bit less right in there. And so that's what was different in 2018. We're not seeing that here either, right? And the other thing she talks about here, I'll just kind of try to rephrase, and I hope I do it justice. But we do have this video available in its entirety on our channel for you guys want to go back and look at this lava chemistry in more detail.
We'll add that to the description of this video. Yeah,
sounds good. Yeah, we have both a full talk, and I think we might have like a highlights version as well. But in any case, the open symbols over here are actually the rims of these crystals, and so they actually measure the distance, the difference in composition from the rim to the core of these crystals. And you can see that the core might have come from deeper, and as it's traveling through cooler magma, it might actually grow a rim on it. So that's why it's important to measure that. And you actually can then tell something about the path of the magma. And so the reason I show this here is because I want to come back to the Volcano Watch. And in a Volcano Watch, they are saying that the crystals grew in these relatively shallow depths, up to a few kilometers. That's that shallow chamber. And they're also saying they're also chemically homogeneous, meaning there's no changes in forcerite content from the middle to the rim. So no mixing between magma that's hotter and colder, right? So what they're showing is, if I can now go back to this diagram, and now we don't need the east rift for what's happening now, right? We have our summit chamber over here, and we have a pathway over here, and we know magma's coming from here and up. But what's happening is getting pushed from below. It's getting pushed from below over here, and then this is pushing up over here, and then this is pushing up over here. And what's coming out is this stuff, like it always does, you know. So what they're saying is it's not like a giant influx that's come in. It's been a slow buildup over time. One thing I can kind of point out, kind of following up on that, is if I go to this extra figure that came in this paper, they actually look at just Pu'o olivine and just Halemaumau olivine cores, the middle of the crystals, right? And so you can kind of see forcerite composition and how many were on that side, right? So black is Pu'o falls mostly in the 78 to 79 forcerite range, with some 76, 77, and also some in the 80, 81, right? You can see Pu'o is all entirely in the 80 to 81, close to 30 samples, every single one, 80, 81, and nothing in 82, right? So in fact, if we have an 82 right now, we actually are slightly on a hotter end right there, slightly hotter. Not hot enough that we had some giant batch come in and push everything out of the way, but maybe that actually is being heated from that whole domino effect from the bottom up, right? From, once again, from down here being hotter, and then that makes this hotter, and then this pushes up and it makes this hotter, and it makes this hotter, right? And all this material that we know had actually gone to collapse and draining in 2018 then got pushed back up, right? So there's definitely a lot of heat to be had as it's getting pushed that whole distance all the way back up over there. Even if it isn't this magma itself, And so that's kind of one of the big questions here, is if I go back and I read this volcano watch, it's not quite clear to me exactly when these samples are from, because they say here, shortly after the first Tephra erupted on the 20th and 21st of December, HVO worked with Microprobe Lab at Mauna Loa to measure. So it sounds like these samples are from just December 20th and 21st. I'm not quite clear. I'm still awaiting some answer on that. But if so, that's important because, as we've seen over here, we can have a clear change over time, right? Even if you start off over here, you could still, 20 days into an eruption, then suddenly show that hotter signal, right? And so it's been 20 days now. I'd like to see if the data we have now is from 20 days in, or is it from just this initial part over here? And do we have a similar pattern where we have first plots over here, and then does it later start showing these mixing values all the way up and down? And that's what I don't know. So that's why I say maybe just the beginning of the story. Maybe we're only seeing days 0 and 1 if it's the 20th and 21st right there. Yeah, and so what it means in the grand scheme of things is we still have to wait and see, right? Where the first lava that came from shallow, as far as I understand it, on the 20th and 21st. And we'll have to see if that's followed by any hotter signal that's come since then. And so we'll have to await the rest of the story there. And that is it for Volcano Watch. And so we can take a few final questions here. If you want to take over, Dan, and give us some questions.
Yeah, really interesting stuff. I went ahead and added a link to the lecture into the description of this video on YouTube. So if anybody wants to watch the full lecture, the clip that he was showcasing is at the very end, and it's broke down into segments, so it's clearly marked for you.
Right. Yeah, and I apologize. The audio wasn't that great, and that's because the recording conditions weren't that great. The USGS video audio was, it's been a little bit of a challenge with the audio on that one. So
yeah, for sure.
Try to clean it up for you guys, and you may have to go back, and if you can't hear it quite well enough, try some other sources there.
So is there, getting into the questions from YouTube, is there a difference in the nature of the earthquakes that would occur on Mauna Loa during inflation versus deflation? Is it reasonable to expect a lull in earthquakes when switching between these?
Sometimes it kind of depends why, right? If the deflation is happening because of something in the Mauna Loa magma chamber, then it might be different than if it's happening on the Kīlauea magma chamber. And so the magma chambers are not connected in any way whatsoever, but the volcanoes do lean on each other, and so they can feel relatively how much elbow room they need as they're swelling or not swelling, swelling or not swelling. So I think the decrease in earthquakes is more so because Kīlauea expanded in October with that Kauiki sequence, and that's something we haven't really shown very recently. But I don't know how easily I can find that as well. But anyways, we do have the Kauiki sequence somewhere. Actually, I think I know where that is. Actually, it is. No, I don't know where that is. I have to find it some other time, guys. We do have an update that we put out. I believe it was in October, right? That we talked about those Kauiki earthquakes and how they might be an adjustment between Mauna Loa and Kīlauea. And so it's basically since then that's what we saw as a signal in Mauna Loa, is that once that adjustment has happened, Mauna Loa was able to essentially continue its magma movement into it without actually spreading at the summit. It had an offsetting signal there. So, but sometimes, if the magma chamber on Mauna Loa itself is the one actually doing the deflating, inflating, and then you can have more earthquakes with more inflation, building to an eruption. That's one of the things we're looking for, is that kind of thing. That's what we saw on Kīlauea. If you go back to our updates, and from October to November to December, we were saying, yeah, Mauna Loa is quiet, but look at Kīlauea. Kīlauea's rift zones are the ones showing all the earthquakes. Kīlauea is the one that's pressurized and ready to erupt sooner than later. We didn't know when, but we knew sooner than later.
Right. So the next questions are kind of about Pahala and the deep earthquakes down there. Jennifer from Facebook is highlighting that the distribution of the earthquakes that have been seen in the past week have been more offshore than maybe we're used to. A little bit towards Loihi. And she was wondering about that, just in general, what's going on in that area.
Well, so over the last day, they're all onshore. Let me just include the last 7 days. Here we can see that there are more of these offshore events over here, right? And so the whole area of the rift zone, I'm sorry, of the hotspot is fairly large. And let's see, I wasn't necessarily going to. Give me a second here. Let me see what I can find that I had that I was working on. And let me throw something else up on here. For you guys, let's throw this one in here.
Here, I'm going to send you an image on the Telegram, and it's the historical activity in that area. And it does show that the area that we're seeing these earthquakes now are within the area that is considered Pahala earthquakes.
Mm-hmm.
This was the one that we posted about 2 years ago when the earthquakes were being weird down Pahala.
Okay, let's put that one up for you guys to see. All right, so there are different kinds of earthquakes too, right? So yeah, here's the image that we put up before, and so that Pahala zone over here does extend offshore, right? And there are earthquakes that have more tremor. The kind of red zone is where you have that long period tremor, which is also an interesting part of the different kinds of earthquakes which occur down there. And when we feel these earthquakes, even island-wide, they feel a little different than other earthquakes we felt. I don't know if those of you guys actually are able to feel earthquakes or lucky enough or, have that sensitivity. So it is certainly within that normal region, right? And what I was kind of trying to bring up here before is this image, which is a compilation of different data of where you see the hotspot, and kind of what this is meant to be. Essentially, this bullseye image right here is where the hotspot is the hottest and kind of where it trails off. And so it's asymmetrical in a sense where it does drag off as a plate moves off in this northwest direction. It does pull the hotspot along with it, right? So you do see like a zone that's hotter all the way over here, right? But the actual core of the hotspot is thought to be a little offshore here, right? So when we're looking at those offshore earthquakes, we're probably looking at directly above this zone before it actually turns and moves over in this direction over here. And let me see if I can find another image for that. Give me a minute here, or a little less, I will. I had found a good one of these that I wanted to share at some point, but apparently today is the day. Okay, here it is. Let's throw this one on here. And then show you guys there how they imagine that this actually, how it hits the bottom of the crust and then kind of drags off in a plate movement direction like that, right? It's kind of this asymmetrical mushroom head, right? So the plate moves off in that direction, and so you have your growing volcanoes at the front end, like Loihi would be somewhere over here. And then as you move over this way, you have your main shield stage, and eventually you can have volcanoes kind of far off the hotspot that can go through rejuvenation stage, even with some melt that comes up through the crust from the bottom of this pathway over here, right? These kind of bottom pathways. So all this to say that offshore is as normal as anything else. It's kind of interesting to see those patterns. And one thing that we mentioned in our last update was that it may be that we see different zonations. There might be like a Kīlauea zone where we see more tremor, and there might be a Loihi zone, or there might be a Mauna Loa zone, or that's something where I'm not sure exactly where those boundaries are exactly, but there is research happening on that front right now. We do know that.
Sorry, I was muted. So getting into final questions that we have given to us. The still focusing on Pahala though. So correlations between Valhalla deep earthquakes and surface activity. If we see earthquakes getting stronger near the coast there, near Valhalla, does that mean that fresher, hotter magma is moving towards shallow?
No, it's all about the depth, really, rather than location on a map. And so if we look at these, it's more about, even these ones that appear to be on shore, they're underneath, they're 30 kilometers down or 20 miles down. So they're below all this volcanic pile. They're actually like that down in the upper part of the mantle there, right? So it's not even the crust anymore. It's kind of below all that. So it's a whole different kind of animal. And there's magma everywhere down there. The whole mantle is magma essentially, right? So there's nothing unusual. It's more about it moving through some pathway where it's resonating and causing the earthquakes. That's the kind of unusual part of it. And then that has to do with how it connects into the crust that's riding above it, right? And so that's really it. It's all at the base of the crust, and all we worry about as far as eruptions is when it's coming shallow. And the places that come shallow are not a surprise to us. We can look at the map and we can kind of see where all the flows are, right? They surround all the rift zones. The rift zones are the shallow pathways, and so when it comes to shallow pathways, it's always rift zones are what we talk about, right? That's why we refer to the rift zones so much. Right, I kind of drew a north one over here because there's a north flow of these radial vents kind of form the third side of this 120-degree split of Mauna Loa right over there. Right, Kīlauea, southwest rift, and southeast rift going off in these directions. That's where it comes up shallow. So if earthquakes happen in those areas, then it comes up. There's no sign of eruption coming up anywhere along the coast here, pretty much ever. Right, there are the Ninola Hills, which are some remnant of an old piece of Mauna Loa caldera, possibly. But that's when the summit of the volcano was all the way over here, when the volcano was much smaller and there was some kind of collapse over in that direction. So those are kind of more of a curiosity than they are an actual active recent lava threat. So there's really no lava does not come up in the ground in there. It comes up over here in the southwest rift of Kīlauea and over here in the southwest rift of Mauna Loa. So if you're in the Pahala area, what you worry about is one of these flows going long enough to get down in your direction, like that. I do want to kind of mention as well, we did do a whole interview with Brian Shiro, USGS seismologist, and that is also on our channel. We could probably put a link up to that, where we go into, we actually ask him all about this topic.
Right. And one day we should probably go through the Truesdale Mauna Loa inundation zones. Mm-hmm. And kind of showcase what we've been able to glean from those, because those are really, a good way to compartmentalize Mauna Loa, because otherwise it becomes a giant roulette wheel with no indication of where your number is, right, or anything like that. And when we look at like just the map that you have up and the inundation zone that leads to Pahala, from Mauna Loa, mm-hmm, there really hasn't been a flow that's gotten that close in the past 750 years. Like they've come down a little bit, but when you look at like the 1950 flow on the other side, that from the southwest rift that fell west, it's significantly different. Like just and it also shows in the Truesdale inundation zone risk analysis on it.
Right.
So maybe one day we'll go through that again. But yeah, the last question in general from YouTube. So what does it look like? It's just going to be pretty calm right now?
Yeah, so we're kind of waiting to see if the deflation-inflation cycle that's come up again is going to stay inflating, or if it might come back down and do deflation-inflation, long-term deflation. That's kind of the question now, is how long can this thing peter out? Because it has been doing that. Yeah. It has been kind of, slowing down and not slowing down. And we saw kind of a batch of fresher magma come up, it seemed like, last week. So will it do that again? And if so, how many times will it do that, right? We saw in 2018, it was certainly a whole different setup, but seeing cycling is not an indication of it keeping going, nor is it an indication of it being over necessarily. It could just, it doesn't necessarily lead itself one way or the other, right? So we have to just kind of wait and see what the trend is beyond the cycling as well. Yeah, and so I did find here the inundation zone, right? So this is the map of the Pahala one is the pink Pahala town is right in here. And so this pink swath would tell you where lava would come from. And so you follow that all the way up here, and you find that it's up here at this 3,100 meter elevation. Now that's the part of the rift zone we have to erupt of Mauna Loa, up by Sulphur Cone and Red Cone, and have to flow down for a long way to actually get all the way over here. So there have been flows that came from here, but they all petered out somewhere in here,
right.
Somewhere in here.
And there was one thing to add in that when you're showcasing it, you're drawing the lines across the rift zone. It only really following that direction would only take roughly half of the rift zone. If it erupts on the other side, you expect it to go north or west.
It's true. It does go off in this direction as well. Yeah, exactly. Yeah, as well as this direction. And there's a lot of topography in here with cinder cones, and so you could get a flow, flow that goes like this, and it goes over here and it goes off this way, or there's some funny stuff that could happen in there, and that's kind of why they have it as a whole zone and not like a distinct fall line, right? Like the continental divide or anything like that, because it can actually form its own topography. Once it leaves this zone, that's when they say, okay, if it leaves this zone and it's pink, now we know it's going towards Pahala, and it's not going towards Ninole, for example. That's what these maps are for, right? For that kind of emergency planning. So.
Yep. And that does it for questions. Again, we're brought to you by Hawaii Tracker, hawaiitracker.com. Please consider sharing this video. And slap that like button.
Mahalo, you guys. Thanks for joining us one more time. We'll come back to you guys after the weekend and bring you guys a weekend recap. And we will continue our coverage of Kīlauea, and we'll try to put out any more interesting stuff, maybe in shorter format, more frequently, and kind of save our more in-depth discussions for our live updates like we're doing right now. So mahalo, you guys. On behalf of Hawaii Tracker, for Dane DuPont, I'm Philip Ong. Aloha.